In today's lecture, we will introduce the del operator and work out what gradient of a function is. The del operator is given by inverted triangle with an arrow on top, and it is defined as I dou by dou x plus j dou by dou y plus k dou by dou z. I, j and k are the unit vectors along the x, y and z direction. And this del operator is the three-dimensional del operator in Cartesian coordinate system. The del operator in two dimension can be written as I dou by dou x plus j dou by dou y. Or depending on the variables in your function, we could also define the two-dimensional del operator as j dou by dou y plus k dou by dou z. So I hope you get the idea of the two-dimensional del operator. From here it is clear that the one-dimensional del operator is nothing but the ordinary derivative. I could write I d by dx in one dimension, or I could also write del equal to j d by dy. Now let's look at the gradient operation of a function. The gradient of a function is written as del operator acting on f, and it is defined as I dou f by dou x plus j dou f by dou y plus k dou f by dou z. Let us look at an example to cement this idea. Example 1. Our function f x y z is given by x square y cube z to the power 4. We want to calculate gradient of f. So therefore I dou x square y cube z to the power 4 by dou x plus j dou by dou y x square y cube z to the power 4 plus k dou by dou z x square y cube z to the power 4. The answer is 2x y cube z to the power 4 plus j 3x square y square z to the power 4 plus k 4x square y cube z to the power 3. Let's look at one more example. Example 2. This time let f equal to exponential of x sine y and log z. Gradient of f equal to I dou by dou x exponential x sine y log z plus j dou f by dou y, where f is this. I'm using this shorthand notation here for the sake of brevity of this video. So therefore I get I exponential x derivative is exponential x sine y log z plus j Partial derivative of f with respect to y gives me exponential of x cos y log z. And finally, k times exponential of x sine y divided by z, because derivative of log z is 1 over z. Notice how the gradient operator takes in a function and gives me a vector. Let us understand the geometrical interpretation of gradient of a function. Geometrical interpretation. If f is a function of x, y, and z, then the gradient of f gives me the direction of the maximum increase of f. Because gradient of f is a vector and grad f will give me that particular direction in which the function f changes in a maximum manner. And if we calculate the magnitude of f, this will give me the slope of the maximum increase of x, increase of f. Now let us look at an application of gradient. Gradient is very useful in physics, and if you have a function f which is equal to the potential at point x, y, z, then if we take the gradient of the potential, you get the electric field at point x, y, z. So therefore, electric field at point x, y, z is equal to minus gradient of v. This minus sign is very important. It must be mentioned here that this v is not the potential energy, but rather the potential.